Okay, so I'm just going to put up basically the key results that we end up working with in 10.3 so that we then can practice working with them and thinking about them. So one was that we can get the slope of a tangent. And that still is dy dx. But I'm going to point out, add to the notation here a little bit to write and point out that this is going to be a function of theta. So we're getting the slope of the tangent, the dy dx, but we're expressing it with a formula where you plug in theta and see what you get. And if we
this is now 10.3 stuff, right?
Yes, thank you. Let me
Okay.
put a notation to that. You're absolutely right. So this is 10.3 stuff. Okay, so so if we have r is equal to some function of theta, like the example we just had, it was 4 sine of 2 theta, whatever it is, it's some formula in theta for r. Then the slope of a tangent to a point on that polar graph would be the derivative of that f function evaluated at some particular theta point times sine theta plus the function times cosine theta divided by the same thing where we make it a minus and we flip the sine and the cosine just to recognize the pattern. So it's still the derivative of the function, but now times cosine, now with a minus and still the function, but now times sine. And so this is just the formula. And so you'll have problems where you figure out the slope of a tangent by plugging into this formula, or you set up the formula and set it equal to 0 to see when you might have a tangent line with a slope of 0, meaning a horizontal tangent line, stuff like that. Then we also have the area of a polar graph. And again, since a polar graph emanates from the origin, actually, if I write it here, I'm about to cover up the middle of my graphing system, so I'm going to remove this a little bit. So since our graph, is an arc that emanates from the origin, like for example, the leaf that we just saw, that you're sort of sweeping out things away from the origin, the kind of area that we're talking about is contained within one of these, trapped by these as it's swept out away from the origin and perhaps returns or doesn't actually come from the origin, whatever. But nonetheless, it's not the area under a curve thinking from left to the right, it's area within the curve away from the origin. All right, so having tried to describe that, then we can have the area contained by r equals f of theta. So then we have an integral between two angles from alpha to beta of 1/2 of whatever the function in theta is squared d theta. Nice simple formula based on the area of a sector. So let's give I'll just put up the page references for these just because these are fundamental. So this is on page 733. And as I mentioned in my little videos, the tangent line is only discussed for 2 pages, including example. And then you get about 3.5 pages for the area, but the area function is, the formula is defined on page 735. And that's what they do in 10.3. So 10.3 is a shorter section, but still. Okay, so let's try an example of something. Maybe I'll put up something from back in the book, maybe. So again, this is for you to try. I'm going to put it up here, and then we'll take a couple of minutes to see if people have questions, but give you guys a chance to try it. So on page 738, you have an exercise. We'll just start number 5, just to wrap your minds around it. And it says, find the slope of the line tangent to the following polar curve at the given point. Find tangent to r equals 1 minus sine theta at the point 1/2 pi over 6. So formula's right here if you want to just use it as it's written, but give this a try or speak up if you have a question.
So on the Cartesian coordinate system, you would use your point with the formula to find your tangent line, but I'm trying to figure out what it would be here. It wouldn't be the same thing, would it?
Well, the slope is the slope. It's the rise over the run. But since the rise over the run is an expression about the change in x and y, we would normally expect that we'd want an equation of a tangent line in x and y in Cartesian. So if they ask for the equation of the line, they're probably going to ask for it in Cartesian. Now, we can have equations for lines in polar, but that only works nicely usually if the lines are radial lines to the origin, because then it's just like theta equals pi over 2 or something like that.
Okay.
So I have a feeling that they won't, in general, have problems where they ask for the equation of the tangent line. They'll just ask for the slope, because the slope is an important concept anyway. Without the equation of the line, the slope is basically saying if you continued along the graph at that point, what direction would you be going? It's a directional issue. It'll show up a little bit more in like third semester calculus more clearly. But in general, I think at this point, really all you got to do is use the formula and come up with a slope.
Yeah. But if we were to find the line itself, we could just use the polar points and then just change them to Cartesian. Yeah,
yes.
Cartesian.
To get on a line in Cartesian coordinates, you'd have to convert the point over, again, with the little formula for x and y that we gave on the page previously. So it's pretty straightforward conversion. And then use that point and the slope you got to come up with the Cartesian equation for the line. So looking to see if anybody else is able to come up with an answer or ask a question. I hate to be a bearer of bad news, but the book has a different answer than the one that we've had provided so far. So let's give you guys some more time to work with this or ask questions.
I'm not sure if I'm doing it right either. How exactly do we involve the points or the point at 1/2 and pi over 6?
Well, since that's the point of tangency, that's the theta value you use in the derivative formula. So really the only thing you need from that point is the theta value, which is pi over 6. Now, of course, the fact that you also know that when you plug pi over 6 into the function, you get 1/2, since that's the r value of the point of tangency. Well, then that's giving you the value of the function at theta, which is these two parts I'm circling up here in the formula. So those two are going to be 1/2 because that's the formula with the theta value plugged in. And then you have to plug that theta value into the sine, the cosine, and the derivative of the function, and then evaluate the ratio.
I got an answer.
What'd you get?
I got 0.
Well, you and the book are in agreement, so I'm going to put 2 check marks there. And the book's check gets a little heavy. It's a little... I mean, not to say your opinion isn't valuable.
I thought it was wrong, like I was plugging in something, but maybe like you can have a slope of 0, that's possible, so I just thought I would say it.
And well, you're right. That's what the book says. So what would you say about the way the line looks if it has a slope of 0? Do you remember what that means?
Is it horizontal?
Exactly. I mean, that was a key point that we looked for a lot of times because that often was a max or a min location back in Calc 1, right? So horizontal sloping 0 is actually not only something that can happen, but a lot of times you look for where does that happen. You actually set the derivative equal to 0 and then solve to find out where that happens. And you'll see a lot of these problems where they ask you to do the same thing. Not only will they just say, find the slope at a particular point, but they could say, find the formula for the slope and set it equal to 0 to see where the graph has horizontal tangent lines. In fact, there are problems like that as well. So yeah, let's see if some other people can come up with their own answer. I'm thinking 0 is the right answer. And so see if you can get there. And if not, try to ask a question.
So we would take the 1/2 and convert it to Cartesian, right?
I don't think we need to do any converting of anything in this problem.
Okay.
Since, yes, I mean, you might have an idea that's good to do in some kinds of problems, but all they want is the tangent slope.
Okay.
And that just means apply this formula.
Okay. Right.
Is that okay? Okay, I can see we are down to about 17 minutes left. So I think one of the ways to see that you would get 0, for those who are still working with this a little bit, is that when you plug in pi over 6, the function gives you 1/2. So that means that f of theta is 1/2 right here in the formula. And cosine of pi over 6 is square root of 3 over 2. So that would be that product. And then sine of pi over 6 is 1/2. So that's this part of the formula. And then the derivative of the function, since the function is 1 minus sine, the derivative of the function would be minus cosine. And if I plug pi over 6 into cosine, I get 3 over 2. So if I have minus that, then that factor would be negative root 3 over 2. So for the two pairs of products in the top, I have positive 1/2 times root 3 over 2 and negative of 1/2 times root 3 over 2. So that's why we end up getting a 0 when you add that up. And it really doesn't matter what happens in the numerator, in the denominator, because the numerator is 0, so you're going to get a 0. I guess it mattered if you got a 0 on the bottom too, but we don't. All right, so that's why we get 0. 0 is the correct answer, just plugging into the formula. And so let's use our last 15 or so minutes to consider, I don't want to clear all the ink, to consider the area formula. So make a little space here. All right, so let's do this. Give you a quick little example to give this formula a try. So now for area, we're talking about that formula. So one of the examples I did to start of a very simple polar equation is when you have r equals theta. That's like x equals y. You just set the two variables equal to each other. So when you have r equals theta, when theta is 0, r is 0. When theta, again, using these radial lines here, when theta is pi over 6, so is r. So that means by the time I've gone up to an angle of pi, this is pi over 12 actually. When I get up to an angle of pi over 12, then from the origin, I've left pi over 12 spaces, which is like a quarter. So let's see, 1, 2, 3, 4. Let's say this is where 1 is. So pi over 12 is going to be around there. And then pi over 6 will be twice that. And then by the time you get to pi over 2, you're at like 1.5, etc. So you have this where you end up with a spiral. So that's just a quick, crappy reminder of something I did a little bit more carefully in the video I made. But nonetheless, you get a spiral. And so I'm going to restrict just to what we have on the graph here. So let's say 0 is less than or equal to theta is less than or equal to 2 pi. So that's one full revolution, and I'm considering this function. So the task is to find the area enclosed, or the area swept out. So that means you can imagine that as these were being made, this is being swept out. Of course, this is supposed to be at 2 pi, which would be like way out at 6 or something. So this is very drastically not drawn to scale. But you get this spiral, and you want to get the area in the spiral. So that's the goal. So let's give that a try and ask questions. You have questions. The formula is, again, right here.
If you're talking, you're muted.
Thank you. I'm just, while you guys are working, I was trying to make a better graph and remaining silent, but thanks for checking.
I have a question.
Yeah, go ahead.
So is the function that we're considering r equals theta?
Correct. So
Okay.
consider, it says right to the left of the graph, consider r equals theta.
Okay.
0 is less than or equal to pi is less than or equal to 2 pi. And I'm trying to make a better graph of that.
Okay. Thank you. Sorry, I wasn't sure if we were still doing the 1 minus sine theta.
Yeah, my bad.
I'm a bit confused on how we're supposed to set this up. We're using the area by the integral, right? Or
Yes. So on the right there, the area contained by a function r equals f of theta is given by that integral. So it's circled in yellow here, over here, this one.
Mhm.
So that's the formula to get the area. And so you want to apply that to this function over the range indicated. Is that okay?
I
So I got, whenever Christian's done,
Somebody got something?
it's fine. It's fine.
I got 4 pi cubed under 3.
4 pi
Sorry, not under, over 3. Sorry.
cubed over 3 like that.
Yeah.
So there's a possible answer. If someone else gets to the end and wants to share the result, we can compare. I haven't done it yet, so I'll see if I agree after you guys give it a try. Okay, about 5 minutes left. So let me just go ahead and see if I set up the integral. If it makes sense to folks who hadn't quite got there yet. See if I get the same thing as you guys. So the 1/2 is a constant. We can pull that out front. I would have 1/2 the integral. And the alpha to beta is 0 to 2 pi. And then our function is theta, which is squared d theta. So happily, that is not a real complicated integral. It's a theta instead of an x, but other than that. So this would be 1/2 theta cubed over 3 evaluated from 0 to 2 pi. So that means that I get 1/6 multiplying the 2 times the 3 times 2 pi to the 3rd minus 0 to the 3rd, which is just 0. So that means I get 8 pi cubed over 6, which reduces perfectly to 4 pi cubed over 3. So well done to a couple of you who were able to get that done and recognize. If we take a look at this little spiral graph here, it's kind of interesting. I don't know if anybody can recognize it. Looks kind of like a shell, like a hermit crab shell or something like that. There's a lot of things in which polar functions represent the dynamics of what's going on in the real world very, very well. First-person shooters is certainly one big category. So polar is really commonly used. It makes sense whenever you have a centric world where you're standing in the middle and looking from place to place and looking at how far things are away from you. So that makes sense in lots of dynamics. And also, you can see examples that show up geometrically in a polar situation is very, very common. If you look at the graph, it kind of looks like the top-down graph of a globe in terms of a polar graph. So lots of applications for this.